So thank you, Alex, for this really nice introduction to simulations, because that also saves me now to really introduce this issue to you. So this is going to be a talk about a simulation which is trying to analyze galaxies, or proto-clusters at a redshift of about 4, because this is something that has been said is a trouble for simulations to actually model. So, and to start right away, so the simulation I'm going to use here is a full cosmological hydrodynamical simulation box volume, and this is part of the so-called Magneticum pathfinder. So the Magneticum pathfinder, sorry? The Magneticum Pathfinder simulation suite is actually a suite of simulations covering several boxes with different sizes. The biggest box having sizes of more than 2,500 megaparsecs over H, and the smallest box going down to something like 48 megaparsecs over H. And of course, if you have different sizes of the boxes, you also have different resolution of the boxes. So this is the suite of simulations that I have for looking for protoclusters here. And just to give you a little bit of a perspective, Alex already said there's a broad range of simulations that can be actually used, but the thing that maybe is most important at this point is to check what kind of simulation can we actually use to understand this kind of protoclusters that we want to analyze. And that means you have to go for a simulation that actually can manage to make really, really big galaxy clusters at the low redshift of z equals 0. And you can see that you are already in trouble with the existing boxes here, because you can see that basically most of the simulations that you usually talk about don't even reach what we would call our standard coma cluster mass at redshift 0. The good news for us is, of course, that you can see here on the right-hand side that the simulation I'm using for this analysis, box 2b and box 0, this is the Magneticum simulations, and we actually have quite a lot of these coma cluster-like galaxy clusters at redshift 0. So let's take a look what happens at higher redshifts. And one of the things that you can see immediately when you look at this is actually you need these kind of big boxes, because here in all this stars that you can see here, this is the protoclusters that are observed nowadays, and on top of it you can actually see what's the most massive clusters in our simulations, and you can see immediately that with the small boxes you have no chance of actually ever catching any of this kind of protoclusters that you would see at redshift 4. So you really need a big box volume, and this is basically what I'm going to show you here. So the box volume we are settling for is the box 2b volume with 640 megaparsecs over H, and this volume is big enough to have these kind of protoclusters, while at the same time it has enough resolution to really look at the galaxies inside these clusters. So let's take a look at what we find. So going at redshift of 4, we find actually 42 potential protoclusters with a mass above 10 to the 13 solar masses in total halo mass in our simulation. So 42 potential candidates. Now, of course, the selection is a little bit different than in observations, because we only take structures that are already bound here. This would be a bit more if we would ignore the bounding fact and say we just take everything that's randomly assembled in a line of sight direction. But for now, let's take what we really know for sure. This is already a bound potential. And then we can check the different traces that we know from observations. So we can actually check which are the most massive ones. So if bought the 4 most massive ones that we have here in the virial mass from the simulation. You can also check which have the most massive BCGs, and you can see immediately in the red highlights here, this is not the same like the ones with which are the most massive ones in terms of virial mass. You can also look at the richness, which means you check how many galaxies are actually part of this cluster, and that's again a different sample. And then people also use the most star-forming regions, so that means the highest star formation rates seen in this environment. Now, from this 42 clusters with this 4 different kind of tracing mechanisms that we have, let's see what we can actually find. So the first thing to check is, do they look anything like what observations can find at redshift 4? And this is one of the clusters I brought here to you. This is our protocluster with the number 1. And you can see immediately it looks strikingly like what observations actually see. So it's this kind of clumpy structure with a bit of filamentary elongation in different directions. So that's actually something that looks pretty good for now. You can also look at the galaxy population inside this cluster. You can see also immediately they are pretty gas rich. They have actually rotation patterns similar to what is seen as well. And as I said, they are in a bound structure here and similar to, in this case, SPT 234956, which is this protocluster at redshift 4.2, which this cluster actually resembles strikingly. Now for this talk, I want to show you what happens to these protoclusters with redshift and not so much what about the galaxies inside this protocluster. So we can analyze them too, but for this, let's check what actually happens. So here I brought you this figure that you have seen probably before. So this is the virial mass of a halo. This is the redshift. And on top of that, you see all the observed halos that are galaxy protoclusters that I could find. So please bear with me if I forgot some. I'm totally willing to fill this up, but this is what I could find so far in the literature. On top of that, you can actually see here, this is the range of the masses of the 10 most massive ones from our simulation. And you can already see that this is different than what was found originally for the Millennium simulation, which is the striped area from Chiang et al. 2013. Now, what you can see, it doesn't look that bad. Actually, we cover quite the range that is expected to be found in the protocluster mass range with our simulation. Now let's check what the individual protoclusters from our simulations are doing. And here I brought you the 8 galaxy clusters that protoclusters that I had highlighted before. And we can now check what is the tracks depending on the different classifications. So let's start with the most star forming one, because we've heard that protoclusters have extremely high star formation rates. So these are the ones with the 4 most star forming ones in our protocluster sample selected at redshift 4. And what you can see is that they actually spread up quite strongly in the evolution pathways. So while one of them, in this case the red one, actually stays the most massive cluster for quite some time, at around redshift of 2, it goes down and it doesn't even make it into the most massive 10 most massive ones at redshift 0. On the other hand, you have another one which is at redshift 4 pretty massive in star formation already, and you can see that it barely makes it into a cluster only at a redshift of about 1. So this one is one that's actually starving. So having a high star formation rate doesn't really help you in deciding what is it going to be at redshift 0, what you actually look at redshift 4. Similar problem when we look at the total mass. So again, the total mass, these are the most massive ones at redshift 4, and you can see, well, they make it, but not really. Again, none of them manages to be among the 10 most massive ones at all at redshift 0. An even worse tracer is the most massive galaxy. So the most massive galaxy at redshift 4 doesn't tell you anything about how massive it's going to be at redshift 0. And now we have a little bit of a good news, because apparently the richness of the clusters, namely the number of galaxies inside this cluster, this is like the best tracer we could find to guarantee that you at least make something like 10 to the 15 solar masses at redshift 0. So what does it is it in conclusion to take it all together? So this plot shows you again here the virial mass of the cluster at redshift 0, and these are our 4 traces. So here's the virial mass at 4, redshift 4, the BCG mass at redshift 4, the number of galaxies at redshift 4, and the star formation rate. And that's what I showed you before. So neither the total mass nor the BCG mass has anything to do as an indicator for what kind of mass you are acquiring by redshift 0. Similarly, the star formation rate doesn't really help. And for the number of galaxies, well, if you are having a lot of satellites, then actually you can be sure that you are ending up pretty massive. If there's only a few one, well, the game is open again. You can become everything from a starved group into a really massive cluster. And now just look at this one more time. So you can see there's 4 of these clusters down here, which really don't make it even into a galaxy cluster at redshift 0. So there's about 25% of our clusters becoming really massive and about 10% really starving and not ever making it at all. So why is it such a good tracer to know the amount of satellites that you have? Well, it's basically that by this you're tracing the range of accretion that the protocluster is still going to happen. So you basically trace what's coming in along the cosmic filaments. And that's the best tracer you have. If you then look at what is happening for the galaxies in this area, you can also see that they actually collapse pretty quickly. So this kind of collapse happens on a time scale that is actually by redshift of 3. All of our BCGs have, all of our galaxies that are in the protoclusters have collapsed into forming the BCG. This is similar to the work that was shown already by Renahan et al. Prior to this in 2019, but we find exactly the same, independent of all the other features of the protoclusters. The BCGs really quickly assemble, building up what's the BCG's course at redshift of 0. Now, for my last minute, I'm going to point out one more thing that you can do with these kind of evolution tracks. And Alex Savo already told us that cosmology plays quite a crucial role. So lucky for us, our Magneticum Pathfinder runs are not just the boxes I showed you before, but they also have a whole range of different cosmologies, all run in the same resolution as, but with different cosmological parameters. This is work shown already by Singh et al. In 2019. Now, if we look at the different quantities that we see here, one steps out, and especially this is the sigma-8 parameter. And if we now look at the growth of our protoclusters, now even up to a redshift of 7, then you can see that the most massive structures that you find at a given redshift depends strongly on the sigma-8 parameter that is used in the different cosmologies. And as you can see here, from what you guys and the observations are telling us, we can actually say, hey, if we always know at the different redshifts what is the highest mass of a protocluster, we can actually try to refine our sigma-8 parameter from this